Hello and Happy New Year, my dear friends, and welcome to our New Year's special now on using SolidWorks. So, suffice it to say, you have SolidWorks. I'm just going to begin from this point. If you need SolidWorks, please contact me and I can step you through the process. So, SolidWorks, let's go ahead and open it up. So basically, you're going to want both the base SolidWorks and SolidWorks Simulation. So to activate SolidWorks Simulation, you have to go to this Options, Add-ins, and make sure you have SolidWorks Simulation box checked. Click OK, and now we're going to use some of those parts from our previous lesson. So go to File and Open, and we're going to open up the DXF file for the dovetail that we drafted in 3D. So that'll be imported into SolidWorks, and now we have the drawing here. What we have to do now is turn this into a part file for each individual part that we have that moves in the assembly. And the terminology of parts and assemblies will hopefully make sense once you start playing around, but basically we'll want to create a male part and a female part. So go ahead and select one of the parts, here the female. I'm going to delete it from the model, and now all we have is the male part left. We can save this now as just the male part. So I'm going to go and save this in an appropriate location, just in this part. Alright, so I already have it saved here, but I'm going to overwrite it. So for male part, replace it, and you can get the same thing for the female part. So supposing you do that as well, go ahead and create the female part too. And now, once you have both of those, go to New, and we want an assembly, a 3D assembly of multiple parts. So click OK, and what we're going to do is import some of our created part files. So we want our male part, click OK, and then don't worry about the placement. You just want to click the check button, OK, place it there, and now go ahead and, well, it's not going to let you do it quite here. Go back to Assembly tab and then Insert Components. Go to Browse and then get the female part. Add that in, say OK, and there you have your working assembly. Alright, now what we're going to want to do with this is perform a simulation. So you'll need to have the Simulation tab, and this can only be seen if you have that add-ins thing checked off. So go to Simulation, Study Advisor, and add a new study. So here, all we're going to do is a linear static study. We don't need anything more complicated than that. So click OK, and there's some nice wizards included within SolidWorks that will walk you through how to actually perform a variety of different simulations, but I'll give you one instance for this particular model. So first, you'll want to select both of your parts and assign a material property. So apply material up here, and we're going to try something like maybe 4130 annealed steel, which, if you check out the IPS English units, we can see that the actual tensile strength is pretty close to what it should be for basically 4130 steel. Likewise with the yield strength, around 66 KSI. So apply that, close it, and now you should see in this little tab it has the material property specified off to the right. Okay, so the next thing we need to do is apply fixtures. So you can just kind of go down the list until you finally get to the run button, but the fixtures will require some knowledge of static determinacy. So the simplest way to do this is to just kind of select one part. In this case, I'm selecting the male part, and I'm going to constrain the base completely as if it were a fixed condition. So in my Fixtures Advisor, I'm going to be assigning a fixed geometry to this particular this particular surface. So fixed geometry, I'm going to say fixed. Indeed, it already has it set up, and all you have to do is click the checkbox. These little green dots basically mean that that face is constrained in a variety of directions. Both, or rather all, X, Y, and Z directions. So you can do a similar thing to the opposite face, but on the female part, instead of constraining fully, we're only going to constrain these four faces, and we're only going to constrain normal displacements. So what does that mean? All right. Well, basically it means we're going to assign a roller slider constraint. And this is essentially what it looks like. So we're going to allow the surface to slide in the plane of the actual surface, but we're not going to allow it to displace normal to that surface. So if we click OK, basically what we now have is a completely fixed surface here and a collection of surfaces that will allow this particular part to slide axially. So that's precisely what we want for this next part, because now we're going to add a force to this end. And you can select whatever force you particularly desire based on how you've set up your SAP model. Now in SAP you could go into I guess a particular member and observe the actual axial force within the member. Say it's a member in tension, and we'll say maybe you saw that member was let's say maybe 0.75 kips in tension. Well, in that case, all you would do in SolidWorks then is select one of these faces, go to assign a force, and it'll bring this up. Make sure you have IPS English units specified, and it'll specify the value in pounds. So 750 pounds, which is essentially equivalent to, oops, and I have selected an extra face that I don't want, 750 pounds, which for the moment specifies it in compression, but we want to reverse that, so now it's in tension. So 750 pounds in tension. And this will vary based on which different members have different forces. Different connections might be designed differently based on the forces they experience. But for this particular connection, we'll say it'll only ever see a maximum force of 750 pounds. So click OK, and essentially we now have everything we need except for connections. So this is a little confusing because connections implies bolts and things like that. But in this case, our connection is simply a set of contact surfaces. So to specify contact surfaces, make sure that you go to Contact Set here in the Connections Advisor. And what we want is essentially, we'll just say automatically find contact sets in the model. We want all touching faces, and we can find all of them in the model just by, first we have to select which parts we're actually going to be looking at, these two parts, and we're looking at all the contact surfaces between these two parts. Okay, so once we have this checked, we can click this button. It'll find all the contact sets. So there should be a total of 5 contact sets. Here, 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 and here. So that amounts to all of these 5. For instance, this one is that lip face, and then so on. This particular contact, that surface, and this one. So we'll select all of these, and then click this plus button to create contact sets. Now, ensure that you have no penetration, since we don't want any interpenetration of the surfaces. And if we create those, essentially we're good to go. Now, you could include friction, but it's a difficult thing to quantify, so we'll not worry about it for now. Now, if you click the check button, you'll have it all set up. Your model is ready to run. So click the run button, and it'll automatically mesh the part with a tet mesh, and then it'll actually run the linear static solution. But there will be some non-linearity because of the contact constraints. So that's usually what takes the longest time in doing the finite element solution. So it'll go, and occasionally it'll have a conversion plot if you want. Here we go. So here is the final solution. And don't worry too much about the tubes, how much stress the tubes are experiencing, although I suppose in certain circumstances you might want to pay attention to that. But what we're really curious about is the stress distribution inside of our part. So it'll have results for stresses, displacements, and strains. Now, for purposes of demonstration, I'll just look briefly at displacements. Now, interestingly, you can kind of check out displacements in a slightly different way. So I'm going to go and check out a displacement plot. And this is a new displacement plot with a different scaling. I'm going to say automatic, or rather user-defined. Yeah, here we go. This is what I want. And I'm going to do maybe, let's say 50 times. So it'll amplify the displacements by 50. And check it out. So this is more or less what the connection will look like when it's deformed. So you can kind of see the female part kind of bulges out like this, and the male part squeezes in like that. And then various stresses occur as a result. Now, it's also kind of showing some amount of slippage, but I wouldn't worry about this too much at the moment, just because we hadn't assigned any friction, so it's expected that there would be some amount of slippage. However, in reality, the connections would have sufficient friction to prevent that. Now, what we want is stresses. So back to stresses. You can see all the stresses here, the von Mises stresses, are listed in newtons per meter squared. But what we want is a new stress plot in terms of KSI, just because it's easier to read. Now in KSI we can see, the maximum stress, which appears to be occurring kind of in the male part, sort of near the tips. Just because of the way it was deforming, we kind of surmise that that would be the case. And also in the female part, there's some significant stresses on those lips that are kind of bending out. But the maximum stresses are about 47 kips, or rather 47 kips per square inch. Whereas the actual yield strength of steel, or for this particular steel, is just 66 KSI. So in that case, we would have a factor of safety of 66 divided by 4.7, or 47. So that's pretty decent, I'd say, roughly 1.4 or something like that. I don't know. So I would say this connection is sufficiently designed. You could even go back and redesign it so you get a little bit closer and have a slightly smaller factor of safety. You could try a bunch of different material removal techniques to sort of remove material and hopefully improve the efficiency. But more or less, as long as it says that you're not yielding the material, then you probably should be okay. You definitely don't want your material to yield. Unfortunately, there aren't any fracture models included within SolidWorks by default. Fracture is actually an ongoing topic of research in the realm of finite elements, but it still gives you a reasonably good idea. As long as it's not yielding, you should be fine. Okay, well, hopefully this was useful. I will see you guys next time.